Okay, so let's start this lecture. We're going to continue from what we finished at last time. Basically, we talked about the capacitor specifications. Of course, we talked about the capacitance itself, the value of the capacitance, the technology, which is like the way it was manufactured, whether it was made of paper, whether it was made of electrolytic capacitor or mica capacitor or ceramic capacitor or tantalum. So the technology is basically the technology that was used to basically manufacture the capacitance. You have also the package, and the package is exactly the same as we saw before in the resistors. It can be through hole or surface mounted, and it can has different shapes and different sizes and things of that sort. And basically, you have to also specify the package that you want for your circuit. The polarity, sometimes you need a capacitor without polarity, or you need a particular polarity, for example. Okay, so basically you have to specify whether you want to have a capacitor that has a positive terminal and a negative terminal, or basically it doesn't matter. You have to specify the tolerance, meaning that it's plus minus 20%, plus minus 10%, whatever. You want to also include a working voltage, which is the maximum voltage that you can apply across the terminals of the capacitor. Basically, this can be like 100 volts, like 20 to 150 volts. So the regular ones that you see in the lab are about 25 volts. So you have to make sure that you have a working voltage that is multiple times the maximum voltage in your circuit, so that you don't have any problems like the ones that we saw last time. You remember the accidents that we saw, the explosion of capacitors. Just make sure that you choose a working voltage that is high enough to avoid having problems like this. The temperature coefficient is not that important, but actually, like any other electronic component, the temperature affects the value of the capacitance. But this is actually not as severe as it was with resistors, because resistors generate heat, and basically they can heat themselves. For capacitors, they basically get affected by the temperature of the environment, which is basically doesn't have that much variation actually. The DC leakage, as I told you before, basically we have, as if we have a resistance like this, the insulation between the two terminals. Let me go and draw it for you. Basically, we said that the capacitance is just a pair of plates, like this, okay? And you have, basically in the middle between the two, you have some kind of a dielectric or an insulator, basically. Basically, this insulation, the insulation material here, has a very large resistance. But actually, it's not infinity. Meaning that you still have leakage between this and that. You still have current between these two plates, okay? And this current actually depends on the kind of insulation that you're using, but you will definitely have some leakage, okay? And this leakage actually is represented in the parasitic effects here as a resistance like this. So basically, if you charge a capacitor, if we, for example, put like 100 volts on a capacitor and leave it for long enough time, you're gonna go and find this voltage becoming like plus 10, for example, okay? Basically, the leakage between the two plates will basically discharge the capacitor over time. So this is the kind of DC leakage we're talking about. And this actually can be specified so that if you want a capacitor that would last for a long time without leakage, you can actually choose particular technology that can do that. And we talked about the parasitic effects, and basically this is important for the case if you have for example, if you have high frequency or if you have low frequency, it's basically you have to consider that the capacitor has multiple components, not just a capacitor. It's not just like that. So basically you have to consider some of the other components if you're going to have high frequency operation or something like that. Okay. Let's move on with the remainder of the lecture. We have the charge and the voltage. For a given capacitor, basically we find the capacitor by the charge and the voltage across the capacitor itself, the potential difference across the capacitor. If you divide the charge by the potential difference, you will find that this will be a constant for a particular capacitor. And this particular constant is called capacitance. And the units will be farad, the SI units will be farads. You probably heard about this definitely. This comes from this equation. Basically, Q, which is a charge, is equal to C, the capacitance, times the voltage. Okay? So basically, the definition of the unit of capacitance, which is a farad, is the capacitance of a capacitor where if you have 1 coulomb and basically have a voltage difference generated on the capacitor of 1 volt, then the capacitance will be 1 farad. Okay? And this is the SI unit. So basically, if you have an equation and you want to plug in the SI unit for the capacitance, you have to plug it in as farad, not microfarad, not millifarad, not picofarad. It has to be in farads. If we have capacitors placed in parallel or in series in the circuit, basically for the parallel capacitors, you have to consider that the voltage across both capacitors should be the same. So basically here, the condition for the parallel capacitor is that the voltage difference here between these 2 points will have to be the same. So voltage is the same for the 2 capacitors. Here, the Q is the same. Because basically, if you consider this plate and this plate, basically this plate here and this plate here, you have a negative charge here and have a positive charge here. And basically, you cannot have imbalance in the charges. So basically, the total number of charges here should be basically 0. So basically, the amount of negative charges here should be exactly the same as the amount of charges here. So basically, the Q will be the same, because actually the negative here should be equal to the positive here, and the positive here should be equal to the negative here. So basically here, V is the same, here Q is the same. So basically, if you have V the same, then Q1 will be equal, or total Q is equal to Q1 over Q2, or plus Q2. Q is equal to C total times the voltage, and Q1 will be equal to C1 times V, and Q2 is equal to C2 times V, and basically you can take out the voltage values across all of them, and basically it will come down to this equation. So the capacitance of capacitors placed in parallel with each other are basically, is going to basically be the summation of the capacitors, the individual capacitors that are placed in parallel. Here it's going to be a little bit different. Here you have the same Q. So basically the voltage between this point right there, if you talk about, if you talk about this point right there, the total voltage here will be from this point to this point, because basically the voltage has to be across both of them. Okay, so the voltage here will be equal to V1 plus V2. And V1 here will be equal to C1 times Q. A Q times a Q over C1. Q is basically, Q is the common Q. And V2 is equal to Q, the same Q over C2. And basically V total, from these two, V total is equal to V1 plus V2 will be equal to, this will be C total times, or Q times, or over C, will be equal to Q over C1 plus Q over C2. And you can take out the Q values from all of them. You're going to come with this equation here. You're going to find this equation to be correct. Okay. Here, if you want to know exactly how much is V1 or how much or V2, you can actually get it directly from this equation right there. The voltage difference across each one of these capacitors will actually inversely proportion to the capacitance, because basically you can see it right there. V1 is inversely proportional to C1. V2 is inversely proportional to C2. So basically V2 over V1 will be equal to C1 over C2. And V1, if you know exactly how much is the total voltage difference across both of them, is going to be V times C2 over C1 plus C2. Okay, it's exactly the opposite of the potential divider that we saw before in the resistance. Here, instead of having R1 over R1 plus R2, no, it's going to be here C2 over C1 plus C2. We can show that very clearly also. Maybe you can do it on the... Okay. If you consider that we have two capacitors like this. Okay. You have here C1, you have here C2. This is V1, and this is V2. This is V total from here to there. Okay. And Q is the same as we said before. Okay. Basically, if I want to get V1 over V2, this will be equal to Q over C1, and this will be equal to Q over C2. So basically, just Q from here, from there, and basically it's going to be C2 over C1. So if you know that V1 and V2 have a relationship like this, then you know that V1 plus V2 equals to V, total V. If you replace V2, for example, by this equation, from this equation right there, from this equation, V2 is equal to what? V2 is equal to V1 times C1 over C2, right? So basically, if you look at it like this, then you can substitute this here, because this will be function of V1. You will have V1 times 1 plus C1 over C2 is equal to V. This here can be transformed into V1 is equal to V times 1 over this. This actually can be made like this. Just take C2 as a common denominator, and basically this will be C1 plus C2. So basically this will be C2 over C1 plus C2. Is that clear?
Yes.
Yes.
Very simple, very simple,
Yes.
very simple equations. You're just solving two equations together.
Doctor.
Yes.
So it's the opposite of resistors, yes?
Yes, exactly. That's what I was saying, actually. So the potential division here in capacitors has, instead of having C1, it has C2. For V1, it depends on C2 over C1 plus C2, not C1 over C1 plus C2. Okay?
Yeah.
So similarly, V2 will be equal to V times what? Times what?
C1.
1 over C1 plus C2.
Right. Correct. Okay. We have some examples here. Let's try to solve them one by one. We have a capacitance of 80 microfarads here, connected across 500 volt DC supply. Calculate the charge. So basically, the basic equation, Q equals to C times V. You have C here. C is 80 times 10 to the minus 6. And you have the voltage here in volts. So basically, just multiply this by that. And the output would be in what units? Coulombs. And this would be SI units. Okay. Here you have three capacitors having capacitances of 2, 4, and 8 microfarads. Find the total capacitance when they are connected in parallel and in series. Okay. In parallel, it's just a summation, C1 plus C2 plus C3. In series, 1C1 plus 1 over C2 plus 1 over C3 would be equal to 1 over C total. Okay, so here, this is going to be like what, 2, 4, and 8, it's going to be 14 microfarads. This would be what? We can actually, as long as we're talking about the same units, maybe we can just use them exactly the same way. So basically, this is like 1/2, 1/4, 1/8 would be equal to 1 over C. And basically, from this, you get C, and it's going to be in microfarad.
Yes, doctor, clear.
Okay. The third one, if two capacitors having capacitances of 6 and 10 microfarads respectively are connected in series. So basically, let's draw that. Basically, you have C1 and C2 like this. We know that we have V1 here and V2 here, and we have the same Q in both of them. Here, what you need to compute is the voltage difference across each capacitance. So basically, this is the 200 volts. This is a total. This is V1 plus V2. You need to compute V1. V1 from the equation we just developed, we just derived, will be equal to V
C2
times C2, right? C1 plus C2. You already have that. You have that. You have both of them. You can compute V1. And once you get V1, you can either subtract it from V1 plus V2, you can subtract it from here, or you can use a similar equation to compute V2. But just use C1 here instead of C2. Okay? Once you computed any of them, V1 or V2, once we computed V1, for example, Q1 is equal to Q2 is equal to what? C times V, right? C1 times V1, which is equal to C2 times V2. So once you compute here V1, you can use the capacitance of the first capacitor and the voltage that you computed from the first part, and just compute the charge, which is going to be equal for both of them. Q1 will be equal to Q2. Do you have any questions? So just remember that when you have capacitors in parallel, the voltage will be the same. When you have capacitors in series, the charge will be the same. In both of them, the only equation we saw so far is Q equals to C times V. The charge is equal to the capacitance times the voltage. So basically, we use that to do whatever we want here. We can compute anything we want here using just this equation.
Yes, doctor, clear.
A very common concept that you have to think about when you think about capacitors is the electric field. Whenever you're having charges separated by charges from on two different conductors separated by a dielectric, you have an electric field. Okay, so basically, an electric field, each line of force emanates from or terminates in electric charge. So basically, you have a basic electric field is just a bunch of lines going from positive charges to negative charges. Okay, so the conventional direction is from positive to negative charges. So if you have positive charges here on the upper plate, and you have negative charges here on the lower plate, then the electric field will go from the positive to the negative charges. So basically, the direction of the line is that of the force experienced by a positive charge placed at a point in the field. So basically, if I have electric field from positive to negative, if I place a positively charged particle here in the middle, this particle will experience repulsion from the positive charges because they are exactly the same charge, and is going to experience attraction by the negative charges. So basically, there will be a force going in exactly the same direction as the electric field. So basically, the direction of the electric field from the positive to the negative is exactly the same as the direction of the force applied on a positive charge placed in that particular location, in the location where I'm looking at the electric field. The lines of electric force, the lines of electric field never intersect, since the resultant force at any point in the field can have only one direction. We should explain this a little bit better. Imagine that I told you that there is an electric field direction like this. You have electric field going like this, and there is another electric field line going like this. So at this particular point, if you place a particular charge, if you place a positive charge here at this point, will it go this way or that way? You cannot actually have two different forces applied on the same particle. Basically, if you place a particular charge within the electric field, it's going to have only one direction of force applied to it. Okay, so basically you can only have one direction of the field at any given point, meaning that the electric field lines cannot intersect. If they intersect, then this will happen, and this is incorrect. Okay, you cannot have two directions of forces applied on a particular charge. You have only one direction. Okay, so for example here, if you have, for example, line going like this, the other line will have to go like this also in order for it to not intersect with it, and the other line will have to go this way as well. Okay, you cannot have lines going like this, for example. No, you can't. Okay, so the electric field lines go parallel to each other, they never intersect. Okay, let's talk about the insulator in the middle. Assume that we replace that insulator with a conductor. Okay, if I have a conductor in between these two plates, what would happen?
Will short the.
Basically, yes, you shorted out these. Basically, if you have a conductor, then these charges can move freely, and basically they will null each other out. You have a positive charge, a negative charge in a particular conductor, basically they will null themselves out. They basically can move freely. Since they can move freely, they can move to each other because they will attract each other. And once they come together, they will just annihilate each other. Basically, the positive and negative charges will just be a neutral atom, not a positive charge or a negative charge. Okay, so basically will be dissipated. If we have a conductor here, the charges will be dissipated. Okay, so basically the insulator is called a dielectric, and basically it has to be there in order for you to have an electric field. You have to have a dielectric here. If you have a conductor, you will not have an electric field, because basically the charges will dissipate, and basically there will be no force applied on a positively charged particle placed in between them. We have another concept called the electric field density. Electric field density, basically, it's a concept related to the density of the lines in between, or the electric field lines, the density per unit area, basically. So basically, what you're talking about here for the electric field, you have the definition of the electric field flux is basically, or the electric field in general, basically it's the voltage over the distance. If you have a certain voltage between these two plates, over the distance, this will define the electric field. Okay, this is the electric field strength. The electric flux density is related more to the Q and related more to the area, not the voltage or the voltage or the distance between the two plates. So basically, the electric flux density is basically the Q, the charge over the area of the plate. And these two concepts are very different, but they have a very unique relationship to each other that we will learn about in 1 second. If you divide the two, if you divide D by E, this will be Q over A over V over D. This is basically, this is the D, and this is the E. And basically, this will be Q over V here, and this will be D over A. And basically, if you place this like this, basically Q over V is equal to C from what we saw, the equation that we just saw. And this will be equal to C D over A. From this definition, actually, we found that basically this particular quantity is always a constant for a particular dielectric, which is called basically if you have, for example, if you put a space, if you put free air or air in between these two plates, you will find that this is corresponding to the permittivity of free space or epsilon naught. This is a constant, okay? So basically, if you have a particular capacitance that is made up of a plate of area A, and the distance between the two plates of D, the capacitance, the effective capacitance of this particular capacitor will be epsilon naught A over D. Just consider this equation right there, this part of the equation. Just get the C on one side and all the other terms on the other side. So C will be equal to epsilon naught A over D. So this is a very useful equation that is similar to the one that we saw in the resistors. If you remember, the resistance equal to rho L over A, if you remember. This is exactly the same. Here we can define the capacitance in terms of the geometric dimensions of the plates that are used to make up the capacitance. Basically, it's just a constant times A over D. Okay? Epsilon naught is one of the universal constants. It's equal to 8.85 times 10 to the minus 12 farad over meter. This is the SI unit for it. And basically, this is one of the constants that basically, this is one of the universal constants that you should have. Basically, it's well known, and basically you can assume that you will have it for any time you need it. If you have a different dielectric than air, then you will have another term called the relative permittivity. The relative permittivity actually is basically a constant or a factor that changes the absolute permittivity, okay? Or changes the free air or what we just talked about, the free space or air permittivity. You multiply by epsilon r to get the permittivity of any other material. If you have vacuum, it's exactly 1. If you have air, it's very close to 1. Practically consider it as 1. If you consider the dielectric as paper, like what we said before, we can actually manufacture capacitors with paper in between aluminum foils, okay? And basically this would be paper making up the dielectric. Then it's going to be in the range of 2 to 2.5, okay? When you increase, or if you use different materials, you'll find that you have different factors, okay? Notice here that if you have distilled water that water without any salts in the middle, and this is actually, we talked about it before, it actually does not conduct electricity. If you have barium titanate, for example, you have 6,000 plus, okay? So actually the kind of material you're going to use here will determine the range of capacitance values that you're going to end up with. If you look at the equation here, for this equation here, if you have a particular, if you have, for example, a vacuum, okay, you will have this as 1, okay? If you have it at barium titanate, it's going to be like 6,000. This means that for the same dimension, for the same physical dimensions of the capacitance, you will have a value of the capacitance that is 6,000 times the value of the same exact dimensions with air or with vacuum in the middle. Okay, so actually the technology that we talked about, when we talked about, for example, mica capacitors, they are actually capacitors that use mica as their dielectric material. Okay, and if you, for example, you have other material like the barium titanate, for example, is used to get much larger values for the capacitance. Okay. For the relative permittivity, it's just the ratio of epsilon, the actual epsilon that you're going to use in the equation, which has the units of, that we just saw before, farad meter. Basically, this is actually is equal to epsilon naught, epsilon r. Epsilon r is just a factor that is dimensionless, doesn't have any units, because it's a ratio. Basically, epsilon r is equal to epsilon over epsilon naught. And both of them have the same units. So basically, the units here will just cancel each other out. So basically, this is just a factor, okay, that doesn't have any dimensions or any units. Okay, so whenever you have a problem and you're trying to compute the capacitance of a particular capacitor with given dimensions, area and distance and things of that sort, the distance between the plates, you need to know epsilon r in order for you to be able to compute the capacitance of this particular capacitor. You don't have to get epsilon, you usually get epsilon r only, okay? So basically this is what is given. Epsilon naught is a constant that you assume that you will have it, okay? So basically in the exam, even if you have the exam as open notes as we said before, either I will provide it for you in the paper, or you should actually have it with you in your notes so that you can use it. But usually you're not given epsilon, you're given only epsilon r, okay? Assuming that epsilon naught is always present. Some calculators actually have the value of epsilon naught present on the calculator itself. So basically, regardless of the way you have epsilon naught, you can just use it and use the epsilon r in the problem and compute the capacitance. If you have multiple plate capacitors like this, for example, basically you will have capacitance between each two of the plates that are shown. So basically this will act as as multiple capacitors connected you have this between these two, you have capacitance, and you have capacitance here, you have capacitance here, you have capacitance here, here, and so on. And given that you have one end here and one end there, and basically this plate and basically this is connected here and this is connected there, basically they act like n parallel plates. But actually they are n parallel plates, but they make up n-1 capacitors. See here you have 1, 2, 3, 4, 5, 6, 7. The number of capacitors you have is a little less. You have capacitance here, 2, 3, 4, 5, 6. So we have only n-1 capacitors from n plates. Okay, whenever you have n plates, you have n-1 capacitors. So the capacitance will simply be epsilon naught, epsilon r, A over D. This is the capacitance of one of them. Okay? And you multiply that by n-1 to get the total capacitance of all of them together. Is that clear?
Doctor, can you repeat that?
Okay. Here you have, basically you have n plates. You have 1, 2, 3, 4, 5, 6, 7. The number of capacitors here, as we said before, the definition of a capacitance is two conductors with dielectric in the middle, right? So here, what you're going to have, you have a capacitance between these two, and you have a capacitance between these two, you have a capacitance between these two, you have a capacitance between these two, and these two. We have 1, 2, 3, 4, 5, 6 capacitors, okay, from 7 lines. Because the seventh one, it doesn't have anything here to add a 7th capacitor, okay? So basically, whenever you have n plates, you expect that you will have n-1 capacitors that are equal. They have the same area, they have the same thickness, they have the same epsilon r, but basically they are all placed in parallel. Okay, so basically the capacitance of each one of these, the capacitance, for example, of this one is equal to epsilon naught, epsilon r, A over D, the same equation that we saw before. This is also the same, this is also the same. The total number is n-1. So basically you multiply by n-1 because the capacitance is equal to C1 plus C2 plus and so on. And each one of them is equal to epsilon naught, epsilon r, A over D. So basically it's just a matter of n-1 times the same capacitance, which is epsilon naught, epsilon r, A over D. That clear?
Yes.
Okay. Okay. We have an example here. we have a capacitance made of 7 metal plates, and these seven metal plates so basically you have 7 here connected as in the same figure. I actually placed exactly the same figure that was in the previous page, separated by sheets of mica having a thickness of 0.3 millimeter. This is what? This is what? This is D. The separation distance is D. Okay? And you have this relative permittivity, which is epsilon R, is given as 6. The area is given as 500 centimeters squared. So basically, the C here will be equal to what? Epsilon naught, which is a constant, epsilon R, 6, A, which is equal to 500 what? 10 to the minus what?
Minus 3.
Minus 4.
4, because square.
It's a square, right?
Yeah.
And this here? 10 to the minus what?
3.
Millimeters. Right? This is for one capacitor, okay? You have 7 metal plates. So basically there will be 7 minus 1 parallel capacitors. So basically the total capacitance will be like this. Just multiply by 7 minus 1. Okay?
Yes.
Okay. For this exact example, basically is referring to the same example here. You have 400 volts across here. Okay. Calculate the charge. Okay. How can you compute the charge? You have basically you have here 7 minus 1 parallel capacitors. Effectively, you can draw this as like this, okay? And you have here 400 volts. Here, instead of worrying about the charge on each one of them, just consider the whole thing. You already computed the total capacitance of all of them, right? You have the total capacitance here, and you have the voltage here. So the charge will be simply Q equal to C times V. You have the C from here. This is the total capacitance of all of them. And V is given as 400 volts. So basically, the Q will be equal to C times V. Okay? The electric field strength or potential gradient basically is what we saw before. E is equal to V over D. You have V and you have D from here. This is D. Can compute electric field strength. To compute the flux density is equal to Q over A. Q, you already computed Q from here. And you have your A as the 500 centimeters from there. So you can also compute that. Have any questions? Anything that I need to repeat?
Doctor, from where we can get the value of EU?
Of what?
Previous question. The first question.
You mean epsilon naught?
Epsilon naught,
yes.
actually.
Sorry.
Epsilon naught is it's a constant. It's a universal constant.
Okay.
Okay, universal constant meaning that you should either have it in your notes or just look it up. Okay, it's a universal constant. It's not going to change. It's like the speed of light, for example. Okay, like Planck's constant, whatever. Okay, so basically these are universal constants that are supposed to be there all the time. You should have them, or you should have access to them all the time. Okay, so either you have it from your calculator, from the net, from your notes, or whatever, from the book. You just have it, you use it, and you get it and use it. So absolute note, you will never see absolute note in the problem. Okay, you should have the value from your notes, or basically look it up on the internet, or if you have a calculator that has universal constants, you get it from there. It's up to you.
Okay.
Okay, what about if we have a composite dielectric capacitor? For example, if you have a capacitor that has actually a dielectric that is made up of two different materials. So, for example, you have a plate here and a plate there, and you have a distance d1, a thickness d1 from dielectric A, and a distance d2 from dielectric B. Okay, what would happen then? How can we calculate the capacitance in this case? In this case, actually, what we need to do is to consider this problem as a series capacitors. Basically, when you have capacitors like this, basically you will have as if you have another plate right there. So basically, it's going to be as if you have a capacitance with a dielectric A here, and another capacitance with dielectric B here, and they are connected like this in series. So all the equations for series capacitors will apply here. So if you have C1 equal to this and C2 equal to this, it's exactly the same, but actually have a different epsilon for each one of them. This is epsilon R, and basically we label them here epsilon 1 for the first material and epsilon 2 for the second material, but this actually is epsilon R. And the total capacitance will be just computed from the series capacitance equation. Okay?
Okay.
Now we talk about charging the capacitor. How are we going to charge the capacitor? What is the relationship between the voltage on the capacitor and if you have a particular charging current, what's going to happen? So here, what he has in the textbook is assume that you have a circuit here. Just ignore how this circuit is constructed. Just assume that you have a constant current going through here. So you have here a certain current that is constant. Okay? If you have a constant current, what's going to happen? Okay? Basically, as we all know, the current is equal to dq by dt. Okay? This is the definition of the current, basically. And given that we have Q is equal to C times V, if you take the derivative of the Q here, of the charge here, you will end up with an equation that says I is equal to C dV by dt. Meaning that if you have a constant current here, this is a current. This is the value of the current here. Okay? So if you have a constant current like this, the voltage will simply be, basically if this is constant, then you have dV by dt is equal to a constant, meaning that the voltage itself, since the derivative of the voltage is positive, will basically be just a linear equation, or a linear, will change linearly like this, and the slope here is dV by dt, which is equal to I over C. If you turn off the current, if the current is 0, then the charge will just stop. Basically, if you have I here is equal to 0, then dV by dt is equal to 0, meaning that it's not going to change. The voltage will remain the same. So basically, it's going to remain constant. The basic idea is that when you stop the current, there is no more change in the charge. You're not charging the capacitor anymore. So it's going to keep the last value of the charge and basically continue like this until another change happens. So basically, if you stop the current, if the current is 0 here, this is 0 current, the voltage will be constant. If you change the current to be negative, this is negative now, the current is negative, basically dV by dt will be equal to I over C, will be, since I is negative, the derivative here will be negative. So the value of the voltage will be basically the slope of the voltage will be negative. It's going to go down like this. Okay, it's going to keep going down like this. If I turn off the current when the charge is 0, then it's going to stop with 0 charge and 0 voltage on the capacitor. Is that clear? This is just an example of how to use this equation. Okay, if you put a positive EI, if you put a positive charge or a positive current here, you will have voltage going up. If you have a 0 current, the voltage will remain the same. If you have negative current, then the capacitor will discharge. The voltage will go down. It's going to discharge and the voltage will go down. If you keep going, by the way, it's going to charge the opposite direction, by the way. Okay, if this current goes all the way like this, then it's going to go continue like this and basically charge in the opposite direction. Okay, so basically whenever we need to put an equation for the current or the relationship between the voltage and the current in the capacitor, this is the relationship. This is very similar to V equals to IR in the resistance. Okay, you always need to know the relationship between voltage and current in each one of your components. So here for the capacitance, you will have a derivative. It's not going to be like the voltage itself and the current itself are directly proportional to each other. Here actually, the current and the derivative of the voltage are proportional to each other with proportionality constant equal to the capacitance itself.
So doctor,
yes.
You can say the current will be 0 when it's fully charged for the capacitor?
No, actually, it's going to keep charging infinitely. Ideally, if you have a constant current going all the time, it's going to keep charging without any limits. There is no such thing as fully charged for the capacitor. It's not a battery. Okay, so basically, if you have a capacitance and you have current going through the capacitance, it's going to keep charging until infinity if the current keeps going at the same rate. Okay.
Okay.
Doctor?
Yes.
Even direct current or alternating current the same.
Actually, yeah, I'm talking about a DC current. Alternating is different. Alternating, actually, what's going to happen is that basically in a particular cycle is going to charge, in the other cycle, the negative part of the cycle is going to be discharging, and basically this will leave no charge on the capacitance. Okay, so basically you have, if you have a waveform, an AC waveform is going to have something that looks like this. Okay.
Yeah.
Here you have positive current, and here you have a negative current. Okay. Here you're going to charge. Here you're going to discharge with exactly the same amount. So here you end up here exactly the same way you were here, because you don't have any net charge. This is different from having a current that looks like this, like what we said about before here. Okay, so in this cycle here, you have charge, and here you have discharge. So basically, they cancel each other out. So at the end of the cycle, the total charge, the total gained charge on the capacitor will be exactly 0. So what I was talking about here is if we have a constant current, basically it looks like this. This is the current. See here? It's a constant here, constant positive value here, constant negative value here, constant 0 here. Okay?
So that's the way the capacitor blocks DC, right, doctor?
Yes, basically, like for the DC, basically we're going to talk about it in a short while. But actually, if you have a DC value, it cannot go to the other side because basically it's an open circuit. Basically, you don't have. It's not like a resistance. Okay. Let's talk about it in a little bit now. Okay, because actually this is related to the value of the impedance of the capacitance, which is basically Z is equal to 1 over J omega C. Okay.
Yeah.
You have omega here as 0, then the impedance of the capacitance will be infinity. So basically it impedes DC because basically the impedance at DC will be infinity, ideally infinity. Okay?
Okay.
Okay. Now we're going to talk about interesting parts of this capacitor lecture, which is basically what happens when we have transients. For example, here I have a voltage source, I have a resistance here, I have a capacitance here. At a certain point, I can actually switch that, make that switch go to position A. And when it's in a position A, you have here a voltage, you have a resistance. Basically, there will be charge going through, or current going through the capacitor, charging the capacitor to a certain value. I can actually, at a certain point, I can switch it to position B. So basically, the circuit, including the capacitor, will have a capacitor here with a particular charge and a particular voltage, with a resistance in series in a closed circuit. What's going to happen when that is the case? Okay, we need to know exactly what's going to happen. First of all, we need to know some information about how to compute this in any general form. Okay, there's an equation that I usually give to my students, and we need to apply it here. Basically, maybe I can write it in the other one so that it's in the notes. If you have a particular circuit, a particular capacitor circuit, and this particular capacitor circuit has a resistance, has a capacitance, and might have also like a voltage source, whatever, okay? You usually would like to have the value of the voltage here, VC, or the current going through here, IC, as a function of whatever happens in the circuit. I'll give you an equation, a very simple equation that you can use to solve any such problem without any difficulty, okay? So basically, for example, if you want to have the voltage, or basically let's consider a particular parameter. Let's just call it, maybe you can consider the voltage, okay? VC is equal to V initial minus V final e to the minus T over RC plus V final, okay? Basically, V initial is equal to VC at 0. V final is equal to VC at infinity. And basically, given these values and what's called the time constant, which is basically, this is called the time constant of the circuit, and I'm sure you heard about it before, okay? You can compute any transient that happens in your circuit, okay? Let's take an example, okay? Let's take the example in the actual circuit that we saw just a few minutes ago. Okay, let's just consider a circuit that has basically. Let's just consider this here. You have here like 10 volts. You have a resistance of 1K, a capacitance of 1 microfarad. Okay, and basically consider that you have a switch here that was turned on at t equals to 0. And consider that VC of 0 is equal to 0. Okay, we need to compute VC as a function of time, which is using this equation. Okay, have you seen this equation before, by the way?
Yes. Yes.
Where?
In circuit.
In the circuit. Okay, so let's try to use it to compute the voltage here. You can actually use it for the voltage or the current or whatever. You just plug in here. If you have here a particular value parameter, V or I, you plug in here the corresponding parameters. So VC of t here will be equal to what? VI is equal to what here? V initial is equal to what?
0.
0, right? So it's going to be 0 minus V final. What is the final value? If I leave this circuit forever, what do I expect to have at the end of this time?
0.
No, actually, this will charge until basically there will be current flowing here until the voltage here is exactly equal to the voltage here.
Yeah.
After that, after this capacitor charges to 10 volts, that's it. That basically the current over the resistance here will be 10 minus 10 over R, which is going to be 0, basically. There will be no more charging. So the final value will be 10 volts. The time constant here will be whatever, tau, which is equal to R or C, whatever, okay? And the final value, as we said before, is 10, right? So basically, if you put this equation together, it's going to be like 10, 1 minus e to the minus t over tau. And this will look like what? At t equal to 0, this will be what? 1, right? So it's going to start from 0. At t equals to infinity, this will be what? At infinity, it will be 0, because this is minus e to the minus infinity. So basically, it's going to be here. For example, this is 10 volts. And you have an exponential growth curve going from here to there between these 2 points. Okay, let's do the same exercise for IC, the same exact problem here. Same exact problem for IC. If I talk about IC, the current, okay, what's IC of 0? The current here at 0. This has 0 voltage at the end, at the beginning, right? And you have here 10 volts. So the potential across this resistance will be 10 volts. So IC will be equal to 10 over 1K, right?
Yes.
Yeah.
How about at infinity? IC of infinity. At infinity, as I said before, this will be fully charged. This will have 10 volts here. So you will have 10 volts minus 10 volts across the resistance here. So basically going to be what?
0.
Going to be 0, right? So basically, if you plug these values in, you'll find the equation as IC of T will be equal to I initial, which is 10 over 1000, minus I final, which is 0, times e to the minus t over tau, plus I final, which is 0, which is basically be like 10 over 1000, like 0.01, e to the minus t over tau. Is going to be like exponential decay, like this. Is that clear?
Yes.
Can you use this equation without any problems?
Yes, doctor.
Inshallah.
Okay. So basically what we're going to do here is basically see a lot of examples of that sort. You have, for example, here, there are problems where you actually switch this to this position here at the beginning at t equals to 0, and after a while, you switch back to position B. Okay, for example, if I told you that after 100 milliseconds, okay, so basically at t equal to 0, switch becomes at A. At t equals to 100 milliseconds, switch was changed to B. What's going to happen here? Basically, when you are in this position, you're going to be charging the capacitor. And basically, at 100 milliseconds, whatever the charge here, whatever the voltage here, is going to be basically what's driving the current after you switch this to this position. Okay, so basically the first circuit will look like this. You have supply, I have a resistance, you have a capacitance, and that's it. The second situation here will look like this: a resistance, a capacitance, and that's it. Okay, and you have a certain initial voltage here at the capacitance at 100 milliseconds. Let's try to do that. Let's try to compute that. If you do that now, basically the equation for the voltage will be like this, something like this. This is going to be the voltage waveform if you switch to position A at time t equal to 0, and if you have an initial condition of 0 on the capacitor. Basically at 100 milliseconds, all I have to do is just plug in, basically just plug in t here equal to 100 milliseconds. This will give me the initial voltage for the capacitors. Basically, it's going to be the new initial voltage. basically it's going to be the new initial voltage. VC initial new. Okay. At the start of after 100 milliseconds, whatever the charge here, whatever the voltage here at 100 milliseconds, okay, will be basically the initial voltage of the capacitance, and this voltage here will pass the current in the resistance because you have a circuit, a closed circuit with the resistance in parallel with the capacitor. So basically, let's go and try to solve that in much more detail, and this will be the end of what we are going to do today. So basically, assume that I have a particular circuit. You have 1K, 1000 ohms or 100 ohms. You have 1 microfarad here. And you have the initial condition will have, or basically the basic circuit, the first circuit will be like if you have a 10 volts here and 100 ohms here and 1 microfarad here. This is the basic circuit that you're going to start up with at t equal to 0. And as we saw before, VC of t will be equal to 1 minus e to the minus t over tau, which is base tau is equal to RC, times 10. Since we're not going to wait until infinity, we're going to just basically switch this circuit at t equals to 100 milliseconds to another circuit that looks like this. Okay. What's going to happen here in that new situation is that we have a voltage here that's going to drive the current across the resistance in the opposite direction. So basically, in the first circuit here, the current was moving in this direction right there. In the new circuit here, you have only voltage here on the capacitor that drives the current in the circuit. So basically, if you try to compute the voltage across the capacitance after 100 milliseconds, it's going to be like